All right, so hi USENIX. Allow me to start with a bold statement, being that the future of computing is heterogeneous. So more and more we see that for high performance applications, much of the compute is being outsourced from the general purpose processor or CPU to domain-specific hardware accelerators, which are heavily optimized for specific tasks. And so in this context, FPGAs are interesting because they provide reconfigurable computing, while at the same time they don't face the same lead times and fixed costs that dedicated ASICs do. So we see some demand emerge for FPGAs, and where there's demand, supply automatically follows, and we see cloud service providers like AWS, Alibaba, and Azure providing means for domain-specific hardware acceleration on FPGAs for their customers. Now, of course, the cloud economics still dictate the same model, being let's place as many tenants as possible on the same shared resources, so on the same physical device. And we also know that shared resources may lead to side-channel attacks, like cache attacks, most notably, where an attacker can spy on memory access patterns by potential victims by monitoring their own interaction with the memory hierarchy. And so in the past, we've seen a lot of cache attacks coming from the CPU, so we would say that the domain is relatively well studied. And very recently, over the past 2 years, we've also seen attacks coming out of secondary devices like FPGAs or network interface cards. But in our work, we put forth a new attacker model, being that of a combined attacker who controls both CPU cores as well as one or more secondary devices. So that's the topic of our talk, Double Trouble, combined heterogeneous attacks on non-inclusive cache hierarchies. My name is Antoon Purnal, and this is joint work with Furkan, Turan, and Ingrid Verbauwhede from imec-COSIC at KU Leuven. Now, so how do secondary devices like FPGAs interact with the memory hierarchy? So let's start with some basic preliminaries first. So the object we'll be studying will be recent Intel server processors, so that's the Xeon product line. And like other processors, they have multiple levels of caches. So you have the L1 and L2 cache private to the core and close to the core. And you also have the shared last level cache, which is shared among all the cores. Now, as you move from the CPU to memory, the caches get larger, but also the access time gets larger. And this leads to a timing side channel which an attacker can use to infer memory activity or contention in specific levels of the cache hierarchy. So most attacks in the past have focused on this shared last level cache, which, well, by virtue of it being shared across the cores, obviously. And we've seen now that in recent CPUs, these last level caches or LLCs have become non-inclusive, which is an invariant that they no longer need to carry lines that are also in L1 and L2. And this changes the dynamics in the cache hierarchy, which we'll also give some more insights on. So how do these secondary devices come in now? Well, so to deliver the necessary performance, these FPGAs, network interface cards, and so on are tightly integrated within the memory hierarchy with something called Intel's DDIO technology, which basically routes all the memory traffic of the secondary device through this shared last level cache. And this provides us with a convenient anchor point, and this is the motivation of this work. Now we can look at this last level cache both from the CPU cores through L1 and L2 and from this secondary device, which we will in the paper instantiate as an FPGA. But so FPGA, what's that? So FPGAs, or field programmable gate arrays, provide reconfigurable hardware, and they do so with a huge array of lookup tables and flip-flops. And with that, they can implement arbitrary hardware logic and flexible interconnects between them. And so we see FPGAs coming up as PCIe acceleration cards in the cloud. And for our malicious implementation, the only thing we require are two main building blocks, actually. So one, of course, we need to interact with the memory hierarchy. So we need a way to read and write memory lines. This is going to be DMA, or direct memory access, which we now know is routed through the CPU, okay, so through this last level cache. And since we're doing timing attacks, we'll also need a timing source. And on an FPGA, well, you can implement arbitrary logic, so it's trivial to implement your own timer. This is just a counter. Okay, so secondary devices go through the LLC, but they're actually really second-class citizens in this last level cache or LLC. So if we assume a memory line X, and the secondary device wants to read this line, well, of course, the line gets served to the secondary device, but it's actually not allocated in the LLC. On the other hand, if the secondary device performs a write, it does get allocated in the last level cache, but not anywhere. So it's constrained. So the data can only be pushed to 2 specific ways in this last level cache set, which we call the DDIO region. And so, okay, there's 2 ways, but this is the default case. So with privileges, you can change this setting in an MSR register, and you can change how many ways DDIO uses, which can go up to the full set. But what we assume in this work is the default case, of course, of 2 DDIO ways. Okay, so secondary reads do not allocate in the last level cache. But what about lines that are already there? So if those get read by the secondary device, they're actually not taken into account in any metadata state keeping, okay? So if the secondary device performs a read, 2 lines already there, so if we have lines X0 and X1 currently in the DDIO region, we see that if the secondary device performs a write, this changes the line to be evicted from X0 to X1, which makes sense. This is keeping track of history. But if there's reads, then we find that no history is kept. So it's as if these reads are invisible. They don't change the state. And so finally, since we focus on the non-inclusive LLC, we need to find out, so we need to discover how lines can be moved in and out of this LLC. So basically what the possible cache transactions are. And for this, we use this double view we now have on the last level cache and do some FPGA-assisted reverse engineering. And some of these findings do not fully match with prior work, so we provide supporting experiments as evidence as part of our open source repo. But what we find out is that lines can be moved from the core to the last level cache, of course, by evicting it from L2 or the directory, so this is well known. But also if you access a line from different cores, this also places a copy in the last level cache. And then, of course, if you write to the line, we saw this also installs a copy in the last level cache. The opposite transactions can also occur, so we can move a line from the LLC back to the core by writing to it with the CPU or by reading from it with the CPU. And there, the details depend on what the coherent state is. But all in all, a combined attacker, so an attacker who has access to this LLC from both sides, has very fine-grained control over the cache level in which these lines reside. And so the second part of the paper is applications of this fine-grained control. So we do some new discoveries there. But with the tight time budget, I'm only going to be able to do a speed run. So strap in. Let's look at the eviction set problem first. So this is finding lines that map to the same set in the last level cache, which is a precursor to many cache attacks. And our FPGA accelerator solves this problem in under 200 microseconds, which is several thousands of eviction sets constructed per second, which is between 1 and 3 orders of magnitude faster than prior work. And so the reason why it works at all is because of these invisible reads, and it works even faster because the DDIO region is so small, so you see evictions very rapidly. And this is kind of interesting because this is a new added capability that a combined attacker has, but it arises from the fact that the secondary device is restricted. So not because the secondary device has additional capabilities. So that's quite an interesting dynamic. We also have another DDIO finding. So what if the secondary device writes to a line, but only after it has already been written to by a core? Well, should it still go to the LLC? Well, yes, and we observe that it does, but it's not allocated in this DDIO region that we already know. So there must be some other undocumented structure in this cache, and that's what we found out, and we reverse engineered this region. which we called the DDIO plus region. So we had the liberty of naming it, but actually went with a pretty boring name. And so this is the layout for the default case, but we repeated this reverse engineering effort for all the possible DDIO configurations. And we see this DDIO plus region being consistently there, so this new undocumented region. And for the very large DDIO configurations, we also see some overlap there. So in conclusion, the control for the combined attacker is even more fine-grained than before, because not only can you fix the cache level in which a line is currently mapped, but also the ways in the set in which it currently resides, which is, to our understanding, unprecedented. So we also show in the paper how a combined attacker can evict lines from the cache with very tiny eviction sets. And the key here is to invalidate lines from specific ways, which we now know how to do, right? We also evict shared lines from other sockets and other cores, obviously, without contention on the directory or without flushing, revealing some interesting cache transactions that we exploit in an end-to-end attack on AES. And we also implement a new kind of covert channel where data is encoded in the number of lines that are evicted, as well as whether they are in DDIO, DDIO plus, or whatever the other region. So to conclude the talk, we built an FPGA accelerator for combined cache attacks as a service, which, by the way, if you want to make money, you can sell accelerators on cloud marketplaces, which we obviously didn't, but we do provide our hardware and software POCs in our open source repo. We also conclude that FPGAs are interesting because they are so flexible, so they can bring their own timer, they can run all the time, and the additions we have to do for them to enable cache attacks consume so little resources on the FPGA fabric that they're basically undetectable. So that will be very hard to detect. And another conclusion is that countermeasures for combined attackers are tricky because they arise from restrictions that are already in place on secondary devices, not based on capabilities that are granted to them. So the future of computing is heterogeneous, yes, but let's not underestimate the complexity this brings, and let's revisit the common assumptions we have on microarchitectural attacks and defenses. And with that, I'd like to move on over to the Q&A.